In section 7.7, we're going to learn how to write 3 different kinds of chemical equations. The molecular equation is what we've been doing, and that's considered, we generally think of that as the regular kind of chemical equation. That shows the complete formulas for the reactants and products. Okay, so that's kind of normal. Then we have a complete ionic equation. This complete ionic equation is going to show anything that's aqueous, any ionic compounds that are soluble, we're going to show them as individual ions. So this is more a picture of what the ions are actually doing in solution. So, if you survey this party and see, chloride's mingling and potassium's mingling, then you're going to write them as individual ions because they're not paired up in solution. So we look at our molecular equation, and anything that has AQ as its state, we are going to divide up into ions. We're not going to separate anything that's a solid, a liquid, or a gas. When we do that, we're going to find that we have what are called spectator ions. So think of going to a boxing match. I've never done that because why? Why would you want to? But I know some people like to do that. If you go to a boxing match and you're a spectator, do you come out with a black eye and a bloody nose? Not unless things got really out of control, right? The spectators come out looking much the same as when they went in. They're not affected. The guys in the ring are messed up, right? The spectators are just watching the action. Nothing's going on. You could have spectators at this party too, right? Watching these 2 people make fools of themselves. But the spectators, nothing happens to them. So to simplify the equation, once we've written that complete ionic equation, we may see, potassium was just an ion over here, unattached, and he's still over here, unattached. He was just watching what was going on. Nothing happened to him. So do we really need to even say that he was at the party? No, we don't. And so we take all the spectators out of the equation, and we just write the ones that something happened to. And when we do that, we have what's called a net ionic equation. So this is like your net paycheck after they take out FICA and Medicare and taxes and everything. It's just the amount that you actually get, right? It's different than your gross pay, which is, what they say they're paying you, but then they take all this junk out, right? So the net ionic equation is the bottom line. So the net ionic equation only shows the species that actually participate in the reaction. The word species means a kind or sort of thing. And in chemistry, that means all the different molecules and ions that are in there. So we say species instead of saying molecule, ion, or atom. It's just more convenient. So I think we've got some examples coming up here. So here's a reaction where we've got HBr, which is soluble, reacting with CaOH2, which is soluble, forming H2O, which is a liquid, and CaBr2, which is also soluble. So we're given the balanced molecular equation, and they ask us to write a complete ionic equation and a net ionic equation. So we have to look at the reactants and products in that equation that we're given, and the ones that are aqueous means it's dissolved into ions and they separate, they're mingling. And when I write these, I'm going to skip the AQ for each ion because otherwise it just doesn't fit. On mastering chemistry, they may want you to include those, and so you have to figure out what mastering chemistry wants and give him what he wants. So HBr, it says aqueous, so I'm going to separate that into 2 ions. I always bring the coefficients down because then it saves the step of balancing later, but you can just break them into ions and then balance it at the end. So HBr is going to give us 2 hydrogen ions, and it's going to give us 2 bromide ions. And you have to write the charges here because these are ions, they're not atoms. So 2 HBRs, each HBr comes apart into H plus and Br minus. And since we have two of them, we're going to end up with two H's and two Brs. And then the calcium hydroxide is soluble. So we're going to end up with Ca2 plus and two OH minuses. And then I just do not seem to be able to get this all on one line, so I'm just going to drop down a little bit here. No, actually, I think I can get this one on one line. Let's go for it. 2H2O. That's a liquid. Water's a liquid. So we're not going to break that into ions. 2H2O, liquid. But this last one is aqueous, and so I'm going to get Ca2 plus, and I'm going to get 2 Br minus. So that is the complete ionic equation. This should be balanced. So let's double check. I have two hydrogens. I have two hydrogens over here, and I have two hydrogens hiding over here. So it's a total of 4. And on the right side, I have 2 times 2 is 4 hydrogens. Got 2 bromines and 2 bromines. I've got 1 calcium on this side, 1 calcium on that side. And here I've got 2 oxygens and 2 oxygens. So that's all balanced. Now, to write the net ionic equation, we look at this and see, okay, who was just watching? What species are the same on the reactant and the product side? Well, bromide. There's 2 bromides on the left and 2 bromides on the right. So just like you could cross those out in a math equation, we can cross them out in a chemical equation. He was there, but nothing happened to him. He wasn't part of the chemical reaction. What's the other spectator ion? Calcium. So here's Ca2 plus, and here's Ca2 plus. So we're just going to not write those in our net ionic equation. So now I'm going to copy down the things that are left, and I'm going to include the state symbols here. 2H plus, that's aqueous, plus 2OH minus, that's aqueous. And that gives us 2H2O liquid. So that is a net ionic equation. Is that the best net ionic equation? No. All the coefficients are 2's. Could we simplify that a little bit? Yeah, we've got ratios of 2 to 2 to 2. Well, that's the same as 1 to 1 to 1, right? So ideally, we would get rid of these 2's. Because that's really the simplest bottom line net ionic equation. Any questions? Pardon me? H2O? No, because that's the formula for the compound. So before we crossed out the 2's, it says we've got 2 hydrogen ions reacting with 2 hydroxide ions to form 2 water molecules. And it would be simpler to say we've got 1 hydrogen ion reacting with 1 hydroxide ion to form 1 water molecule. Because we could also say we have 2,000 reacting with 2,000 to make 2,000. And so we've just chosen to always go with the lowest ratio. Question?
How do you know when to cancel the numbers out?
How do you know when to cancel the numbers out? It's like in math. If you have a fraction that's 2/4, you can reduce that, right? Because both of those numbers are divisible by 2. And so that's the same as 1 over 2. So think of these coefficients as, well, you can't really think of them as fractions because there's more than 2. But 2 to 2 to 2 is a ratio. That ratio, all of those numbers are divisible by 2. And so we get 1 to 1 to 1. Okay. What if we had a ratio of 2 to 6 to 4? Could we reduce that? Yeah, all those numbers are divisible by 2. They have a common factor. So if we divide them by 2, we're going to get 2 divided by 1 is 1, and 6 divided by 2 is 3, and 4 divided by 2 is 2. And so those would be our coefficients. On a multiple choice exam, they want the lowest coefficients because that's the best answer, right? So with the higher coefficients, it is balanced. We know what you mean, but that's not the best way to express it. Any other questions?